Okay, well, it's a great pleasure to welcome Des Johnston. He is going to tell us his journeys virtually from Harriet Watt in Edinburgh, and he's going to tell us about the three Plaquette Ising models, subsystem symmetries, and fractons. Okay, thanks, Des. Thanks for agreeing to give the talk.
No problem. Thanks very much, Denjo. Can I just check that people can hear me okay and they can see the shared screen okay? All good, Denjo? Everything good? Okay, I'll kick off then. This talk really is a response to the talk about a month ago, I think, by Patricio Salgado Redoyedo, who was interested in talking about continuum field theories that were related to these fractons, which are quasi-particle excitations that have got some sort of restricted mobility. And in his talk, he kicked off by describing some lattice models which gave rise to these continuum field theories, and he didn't really want to talk about them. And he got a good grilling from Denjo and some of the other members of the audience as a consequence of this. I'm going to do exactly the reverse of that. I'm going to talk about some lattice models. I'm going to start out with classical spin models, and in particular, the 3D Plaquette Ising Model, which at first sight looks like it doesn't have very much to do with the topic of Patricio's seminar a few weeks back. But I'm going to relate that to the X-cubed model, which is a quantum spin model that he gave as an example of something that had these fractonic excitations, these quasi-particles with restricted mobility. And then also, in contradistinction to Patricio, I'm going to say very little about continuum field theories because I know very little about the continuum field theories. In fact, I suspect I knew less than most members of the audience about the X-cubed model and also related models like the toric code. So feel free to grill me on those. Away we go. What am I going to be talking about? I'm going to start out with a particular classical spin model on a 3D cubic lattice. And it's not the standard 3D Ising model. So I've written that down here. We've got a Hamiltonian where we've got a couple of spins that interact along nearest neighbor bonds. So if you have a wee look here, here's a chunk of the 3D cubic lattice. Here are the spins which are living at the vertices of this lattice. And the spins only interact with their nearest neighbors on the cubic lattice. And this beta here is in effect 1 over the temperature. And what we're interested in doing with these sorts of models is we're interested in evaluating a partition function, which is something that looks like this. So we're interested in evaluating a sum over all possible spin configurations of this object. And from this, we can work out things like the magnetization or the energy or the variances of these quantities, things like the specific heat or the magnetic susceptibility. And we know that for the Ising model, both in 2 dimensions and in 3 dimensions, there's a phase transition. So at high temperatures, so if T is large, this beta is small, there's a paramagnetic disordered phase. But at low temperatures, the interaction term here is going to dominate in the Hamiltonian. So the spins are going to prefer to be lined up if I've managed to get all of my pluses and minuses right. So let me just check. There's a minus there. There's a minus there. So the largest contribution in these weights to the spin configurations are going to come whenever I've got a pair of neighboring spins that are lined up. And the question is, how does the system transition between the high temperature disordered phase and a low temperature ordered phase? So if this Hamiltonian was on a 1-dimensional chain, you could solve it exactly. And you could see that there wasn't a sharp phase transition. So this is what Ising did originally. He solved the 1-dimensional Ising model and showed there wasn't anything interesting going on. There was a smooth crossover between the low temperature and the high temperature behavior. Then Onsager came along later and showed that in the 2-dimensional case, there was a continuous phase transition. So there was a low temperature disordered phase, sorry, a low temperature ordered phase, and a high temperature disordered phase, and a phase transition at one particular temperature between these two phases. So the game with any model that looks like this, whether it's the original Ising model or something else, like the Plaquette Ising model I'm going to be talking about, is to twiddle around the external parameters. So in this Ising model example here, I've included an external temperature and also an external field, a biasing field as well. We can twiddle these around and see what the behavior of the system's like. If we're lucky, we might be able to say something analytically. Usually we're not, and we have to do a simulation to see what's going on. So what's the model I'm interested in talking about in particular? It's this guy. So we're still looking at a three-dimensional cubic lattice. Now the Hamiltonian has got 4 spin interactions. So instead of the standard 2-spin interaction that I've got in the usual Ising model, the interactions are around the plaquette of the lattice. They're still classical plus and minus 1 spins. And you'll notice this isn't 3D. And I was going to say Z2 lattice gauge theory, but we're not Americans, so I'll say Z2 lattice gauge theory. It's not 3-dimensional lattice gauge theory where the spins would live on the edges. The spins are still sitting on the vertices of this 3-dimensional lattice. So it's a perfectly kosher lattice spin model, classical lattice spin model. I'll forget about putting in an external field gauge. I'll just have a look at the temperature or the inverse temperature beta. I'll twiddle that around in this model and I'll look and see what the phase structure of the model is. So the objective is to take this Hamiltonian at the top here, which has got plaquette interactions on a 3-dimensional cubic lattice. And when I say evaluate, in this case, we can't solve it exactly on this 3D cubic lattice. What I'm interested in doing is doing a simulation of this and seeing whether there's a disordered phase at high temperatures and an ordered phase at low temperatures and what the nature of the order is in that case. Before I do that, let me just say a little bit about why this model was formulated in the first place. It's got a curious history. Originally, it actually came out of string theory. Savidi and Wegener were interested in forming or in formulating models for surfaces on cubic lattices, where you thought of the surfaces as being spin cluster boundaries. So every time a spin went from a plus to a minus, you put in a plaquette on the dual lattice. So you thought of the spin cluster boundaries in these spin models as being an ensemble of surfaces on your cubic lattice. And they were interested in doing this to try and formulate some sort of continuum string theory that didn't have the sorts of problems that you see with ordinary bosonic string theory, the sorts of divergences that you see with ordinary bosonic string theory. And they observed that if you took a generalized Ising action on this cubic lattice, you could give weights not just to the area of your surfaces. So if you just take a standard Ising model with nearest neighbor interactions, in effect, what you're doing in that case is you're just weighting the area of spin cluster boundaries, because the only time you get some sort of a weight is whenever there's a difference in the spins across a link. But if you allow nearest neighbor, next to nearest neighbor, and plaquette interactions, you can think about weighting intersections between 4 plaquettes. So here's a configuration where I've got 4 plaquettes intersecting each other. I can arrange the interactions in my spin model Hamiltonian to give weights to the intersection of 4 plaquettes and also to right-angled bends whenever 2 plaquettes meet. And if I've got a situation like this, I can think of this as either being 4 intersecting plaquettes or 2 right-angled bends intersecting in 2 different possible ways. And if I do that, the Hamiltonian that I end up with for my generalized Ising model looks like this. So if I want to weight the surfaces of the spin cluster boundaries so that there's some weight for the area, some weight for the number of right angled bends in the surface, the number of edges where two plaquettes meet at right angles, and some weight where four plaquettes intersect each other. I can map between this spin Hamiltonian that's got nearest neighbor, next to nearest neighbor, and plaquette interactions, and this surface Hamiltonian. So it's sufficient to have nearest neighbor, next to nearest neighbor, and plaquette interactions to weight not just the area, which is what you get only for nearest neighbor interactions for spin cluster boundaries, but also edges, right angled bends in your spin cluster boundaries on the cubic lattice, and intersections of four plaquettes in those spin cluster boundaries. So you've got three parameters now to play around with, see what the phase behavior of these models looks like. And there was a lot of work done a good few years ago by Capi, Colangelo, Ganella, and Maritain, who were interested in using these generalized spin models to model things like emulsions and foams on the lattice. So you give different weights to these, and you see what the typical configurations of your spin cluster boundaries look like in that case. One particular class of these models is where you tune out the area.
Just say hello, Maeve. Hello.
Hello.
Hello, how you doing? That's a nice hat there.
Okay.
I'm impressed.
Hi, Maeve. Maeve is a frequent guest here with us,
Nice
and she
to
likes to wear a Mexican hat. So
It's a very nice Mexican
Hi,
hat. Much more
Okay.
impressive than
Thanks,
any
Maeve.
hat. I lost my train of thought. Now I have to admire.
Sorry about that.
No, not to worry. So one thing you can do, let's go back to this, is tune out the area bit of the action completely. That's what you have with the standard nearest neighbor icing model. And you can do that by choosing the coefficients in your generalized icing Hamiltonian to look like this. So that gets rid of the beta A term if you think of the icing Hamiltonian as giving you some weights for your spin cluster boundaries. And this one parameter family of icing models was called, for obscure reasons, gonihedric icing models by Savidi and Wegener whenever they first wrote them down. And they're interesting to investigate because you've got rid of the icing term by this particular choice. You've got rid of the usual area weight for spin cluster boundaries in the standard icing model by this choice of coefficients. And that means you might see different phase behavior from the 3D icing model. So you've tuned away the usual icing critical behavior. What do you see in its place? You can go further. You could make this kappa equal to 0 and end up with the plaquette interaction in 3 dimensions that I started with. So this is the 3D plaquette icing model. What it is a particular example of a class of icing models where you've chosen to not weight the area of spin cluster boundaries whenever you think about the spin cluster boundaries rather than the spins themselves. So the game now is to take this, twiddle around the temperature, and have a look at the critical behavior. And because you've got rid of the standard critical, the standard weighting that you would see from the nearest neighbor 3-dimensional icing model, where you've just got nearest neighbor interactions along an edge, there's the possibility of seeing different critical behavior than you would. The 1/2 here is the bane of my life. Of course, the only thing this does is rescale any beta that you put in front of it. But if you try and compare different authors who've simulated this, they'll all have used different conventions, either with or without the 1/2. And the different authors includes different versions of myself in different papers. So it's very easy to forget the 1/2 here. It doesn't make any difference. All you're doing is rescaling the temperature. But if you're motivated in the unlikely event that you're motivated to ever read any of the literature on this, bear this in mind. Some people put a half in there and some people don't, where the sum includes different papers by the same person. So this is what we're interested in simulating. And what you find when you simulate it, so you're simulating a three-dimensional Plaquette Ising model. The spins live at the vertices of a three-dimensional cubic lattice. The interactions are around the plaquettes of that lattice. They're not just nearest neighbor interactions between pairs of spins. And the three-dimensional Ising model, the standard one with nearest neighbor interactions, has got a continuous phase transition. There are no exact values for the critical exponents, but they're known to a very high degree of precision from numerical simulations. This Plaquette model doesn't have a continuous phase transition. It's got a first order phase transition. So I'll explain what I mean by first and second order phase transitions in a second. Basically, a first order phase transition's got discontinuities in the observables that you'd care to look at, like the energy or the magnetization, whereas a second order or a higher order transition has got continuous changes in such variables. But simulating this beastie on a 3D cubic lattice gives you a strong first order phase transition. So in particular, that means there isn't a continuum limit that you can think of at that point. So here's a couple of caricatures of what you'd expect to see for either a first order transition or a continuous second order transition. So if you're looking at something like a polarization or a magnetization and you're changing the temperature, if you've got a second order transition, that would vanish continuously and disappear at some critical point like this. And I've written as TC on this little figure. If you've got a first order transition, on the other hand, and you were measuring, say, a magnetization, once it got to this TC, transition temperature in this case, it would change discontinuously. And for a second order transition, you'd get divergences in things like the specific heat, which is the variance of the energy, or the susceptibility, which is the variance of the magnetization, the model that you're looking at. So typically, your continuous second order transitions would have continuously vanishing order parameters and divergences in variances. And the game with a second order transition is to find out how things diverge in the case of the variances or vanish in the cases of things like the magnetization. And there are two ways that you can do this. One of them is to think about how things change as you approach this transition temperature between the ordered and the disordered phase. So you could define a scaled distance of your transition temperature, and then in general, for a continuous transition, the correlation length. So you can define a correlation length between your spins in your model. You have a look at how they correlate over different lattice lengths. That would diverge with some critical exponent that's characteristic of the transition. The magnetization would vanish continuously with some exponent, again, that's determined by the transition. And things like the specific heat, that's the variance in the energy, would diverge with some exponent, and the magnetic susceptibility would diverge with some exponent. And there's various scaling relations that relate these exponents. If you're doing numerical simulations, instead of trying to go to the biggest system that you can and having a look at how things change with the temperature, it makes more sense to make use of systems of different size and look at how these quantities here change with the size of your simulated system. So that way you're not throwing away any of the data from the smaller systems. So the idea is, if you've got some system that's of finite size, which you will if you're doing a simulation on a computer, you can't have an infinite size system, the correlation length the biggest correlation length that you can get is going to be roughly the linear size of the system. So let's call that L. So I can use this relation here for the divergence of the correlation length to relate the T and the L. So I just say T to the minus nu is equal to L here. And then I trade in all of the T's in these scaling relations for L's, the linear size of the system that I've got. So what I find is I would expect the magnetization to vanish like this. So now the correlation length exponent appears here as well. And I would expect the specific heat to have a peak that scales like this. And I would expect the susceptibility to have a peak that scales like this. So these M, C, and L are the things that I'd be measuring in any numerical simulation. I'd do this for differently sized systems, and then I'd try and fit these exponents. And that would tell me which particular phase transition I had. So for continuous transitions, the game is to find these exponents. And I do that by simulating systems of different size as carefully as I can with the cleverest algorithms that I can use and extracting these exponents. Great, but that's not what we have here. We've got a first order phase transition. So what do I expect for this Plaquette Ising model if I stick it on a computer and look at the transition instead of in some fictional infinitely sized system, in a system of linear size L sitting on my computer? How do I expect a first order phase transition to scale? There aren't any critical exponents in that case. So I'm not looking for beta, alpha, gamma, and mu, but I still get scaling, a sort of trivial scaling, as we can see from the following arguments. So in a first order phase transition, if you're close to the transition point, what you typically see is phase coexistence. So there'll be a disordered phase and an ordered phase coexisting at the transition point. And if you're doing a simulation, your system jumps between the two, very close to the phase transition point. So here's a time series. I think this is a simulation of a Potts model here. So if you've got a Q state Potts model, that's a bit like an Ising model, but they're now, instead of two different sorts of spins, plus and minus, Q different flavors of spins. And that means that you've got Q possible ground states that it can choose to go into. So what you see is some fraction in one of the ordered phases with some energy, and another fraction in the disordered phase. So as it goes along, it's jumping from the disordered to the ordered phase. And if you plot a histogram of the number of states that you've got, you get something like this. And at the phase transition, there's a couple of peaks with roughly equal height. One for the ordered phase is if there's multiple ordered phases, and one for the disordered phase. So how would you expect something like this to scale if you did a computer simulation of it? Let's skip back here. So you've got a couple of phases. Let's pretend that in the ordered phase, everything's exactly the same. In the disordered phase, everything's exactly the same. And that the transitions between the two are instantaneous. And then try and work out things like the energy in that case. Well, that's a very simple approximation. You've got some fraction of things in, say, an ordered phase. You've got some fraction in the disordered phase. The two fractions, this W0 and 1 minus W0, add up to 1. That's everything. And there's no interaction between the two. So moments of things like the energy are just given by these sums of the separate phases. And if I want to work out something like a variance, a specific heat, so these are moments of the energy here. The specific heat is the variance of the energy. And this is the energy per site that I'm working out here. I simply get a volume scaling. So this is a general expression for the specific heat. And the peak in this expression is where the W0 is equal to the 1 minus W0 is equal to a half. So you've got equally weighted peaks. So at the phase transition point, you'd expect the weight of both of these peaks, one for disordered phases, one for the ordered phase, to be the same. And in that case,
Sorry, if I may. So I was actually just going to ask if you could tell from the histogram where the phase transition has happened, but that's what
yes,
you
you can. There are various ways that you could say that you're seeing the phase transition in your simulation. You could say the peaks have got equal height here in whatever quantity you're looking at, or you could say that they've got equal weight. So the areas under the peaks suitably defined, so you chop them off at some point, is the same.
Okay, so
And you'd get different estimates for your transition point depending on the different quantities that you used. So this is an energy that we're looking at here. You might choose to do this, say, for a magnetization instead, or some other quantity.
yeah. Okay, fantastic.
That gives you an estimate of where your transition point is. And if we assume that we're finding the real infinite volume transition.
Also, I think people model them by two Gaussians.
Yes, that's right. I mean,
which gives you.
That also gives it. So this is one step down from doing that. That's even simpler. If you model it by two Gaussians, you get exactly the same answer, modulo some numerical coefficients in front. It's the same idea. So the maximum of the variance in the energy looks like this. And you can see it's got a trivial volume scaling. So if you've got a first order phase transition, simple-minded arguments like this, and like Denju says, more sophisticated arguments where you model the peaks with a couple of Gaussians, tell you that you see volume scaling for peaks. So there are no critical exponents sitting in here. They're still scaling, but in a way it's trivial. It's just the volume of the system that things are growing by, rather than something that depends on these critical exponents. So for a first order phase transition, there aren't any critical exponents to pull out from your system. There's just this volume scaling, apparently. You can also have a look with a slightly more sophisticated argument at how your estimates of where the transition point sits change with the size of your simulations. And to do this, you have a look at the probability of being in either an ordered state or a disordered state. So the probability of being in an ordered state is this. So the betas are 1 over temperature, throwing away the Boltzmann constant. And the F here is the free energy per unit volume. So I've included a volume factor sitting in front of it. So these are just the usual Boltzmann weights for being in a particular state. And the probability of being in a disordered state looks like this. The time that you'd spend in any one of these states is the W0 and the 1 minus W0, the WD, probability of being in the disordered state. If you've got Q ordered states, you'll need to multiply that by a Q. So something like a Q-state Potts model. So taking these Boltzmann weights, the ratio between the W0, the amount of time that you spend in the ordered state, and the amount of time that you spend in the disordered state is given by this expression here. So let's take a logarithm of both sides and expand it around the infinite volume transition temperature. If I'm sitting at my estimate of the transition temperature, the W0 will be equal to the WD. That's the idea. And I can Taylor expand the free energy. The constant terms will be the same if I'm at the phase transition point. And dF by d beta is just the energy. So if I take the log of this expression, Taylor expand it around the infinite volume transition temperature, I get this. And then I think of this as an equation for beta, which will be my estimate of where the transition temperature sits on my finite volume system. So take these two terms, solve it for beta, and I get this. What's the end result of doing all of that? I get a shift again by 1 over the volume. And the delta here is the change in the energy between the ordered and the disordered state, whatever that happens to be. So what do we learn from these calculations? Peaks in finite size simulations where you've got a first order phase transition go up with the volume, apparently. Our estimates of where that first order phase transition sits shift with 1 over the volume, apparently. And this should be true for any first order phase transition. That's the idea. Except it isn't. And there's an interesting story behind this, so I'll probably go off piste. The first really good simulations, really careful simulations of the Plaquette Ising model on a 3D cubic lattice were done by Wolfhard Janke and a student of his, Marco Müller. The first not very careful simulations were done by me. And what they were interested in doing was improving my simulations and tidying up my estimates of where this first order phase transition was. And whenever they had a look at how the estimate of the first order phase transition point shifted with the size of their simulations, what they found was that it didn't shift as 1 over the volume. It shifted as 1 over L squared. So the lattice volume is L cubed. You do a careful simulation, which I didn't do, but they did. And if you have a look at these graphs, what they're fitting or what they're plotting is the quality of the fits to these two forms for the shift in the estimate of the first order transition point against the minimum and the maximum size of lattices used in the fits. And for our purposes, pink, it started out as red, but it's come out as this horrible pink. Pink is bad, green is good. So if you try and fit the standard scaling form for a first order phase transition for this Plaquette Ising model, it doesn't work. If you fit this, so that they were just playing around to see what fitted well, instead of L cubed, L squared, if you fit that instead, you get a good fit. So the question is, what's going on? So Marco Müller was a PhD student, and they asked me about this, and I made the obvious suggestion that Marco was wrong because he was a PhD student. And he wasn't, he was right, I was wrong. There is a reason for this happening in the Plaquette Ising model. If you have a look at any of the papers involving this, my name goes last because I was wrong, and Marco's name goes first because he was right. So why is this L squared instead of L cubed? Is there anything peculiar about this Plaquette Ising model? And I've included these couple of slides because it allows me to say fukinuki, which I like saying. So this is courtesy of Suzuki. So is there anything strange about the order, about the nature of the transition and the nature of the ground states indeed in the Plaquette Ising model compared with standard Ising models or POTS models, some of which have got first order phase transitions? And the hint comes from switching off one of the couplings in the Plaquette Ising model. I think, I'm not a Japanese speaker, I don't know if there are any Japanese speakers in the audience. Fukinuki was...
Yeah, yes, we have Saki.
Yeah, no mezzanine?
Yeah.
Does that mean no mezzanine? So it was a term that was coined by Suzuki. So he's one of these original guys working in spin glasses and lattice spin models.
Is it the Suzuki finite size scaling?
It is, it's exactly him. So this guy who's been around forever, and he came up with this model way back in the 1970s. And what he was interested in coming up with was quasi-soluble models in 3 dimensions. So our Plaquette Ising model with uniform couplings in all 3 directions isn't solvable. But let's switch off one of the couplings. So let's switch off the mezzanine coupling, the ceiling. So there's no ceiling coupling in these things. There's only this one, the green one, and the blue one. And let's see what we can say about this model. So we're still on a cubic lattice. We've still got classical plus or minus 1 spins, but now we've switched off one of the couplings. What sort of model is this? Well, if you've got free boundary conditions of this model, and the free boundary conditions are important, it gets more complicated if you look at periodic boundary conditions, you can actually transform it into a decoupled stack of ordinary two-dimensional Ising models. It's not immediately apparent. You've started out with Plaquette interactions, but if you take this transformation of the variables, so remember we're starting out with a couple of sigmas here. So if I make a couple of sigmas a single tau, the partition function factorizes with open boundary conditions on the top and the bottom. It doesn't really matter what they are on the sides. And you get this. So this is just a stack of two-dimensional Ising models. And you can see what the order is going to be in this case. Each layer, horizontal layer in this case, can magnetize independently. So I get a sort of smectic order. It's like a caricature of smectic order in this model. So I don't have a director field telling me about polymers and things. I just have a plus and a minus 1. But each one of these planes can magnetize either plus order pointing up or down order. So say orange is plus, gray is pointing down. And it's tempting to think that what's going on with the Plaquette Ising model with uniform couplings, where I switch on the ceiling coupling again, might be something similar to this. So I could think about investigating an order parameter that has a look at planar correlations and seeing if that still is telling me about the phase transition in the case of the uniform 3D Plaquette Ising model. And it is. In fact, you can see this just by considering the ground states of the 3D Plaquette Ising model. You can flip. If you just take a look at a single cube, a cubic lattice, you can flip any one of the faces here without changing the energy because of the nature of the energy. So remember, it's the Hamiltonian is products of spins around plaquettes. If I flipped all of the spins, say, on this top plaquette here, on the top right, from plus to minus, the value of the energy from the top plaquette is unchanged because it's a product of the 4 spins. But the vertical plaquette energies are also unchanged because each of them contain 2 of these spins. So certainly for the ground state, and it's also true that I can flip multiple planes of the spins, because in all cases, I'm always flipping the spins in pairs on each one of the plaquettes. So it's certainly true that for the ground state, where I don't worry about entropic effects, I can flip any plane of spins, even if they're intersecting on the cubic lattice, and it won't change the energy by reference with a ferromagnetic state where all of the spins are pointing in one direction. And if you, where you is Wegener and a student of his, do a low temperature expansion of the model, you can show that this behavior persists into the low temperature phase as well. So the low temperature phase allows you to flip any plane of spins without affecting the energies.
Sorry, may I ask a silly question?
Not at all.
You said in the ground state, you don't need to worry about the entropic.
Yeah, it's only so this argument is only looking at the energy, the Hamiltonian itself. So it's not looking at the sort of number of spins and things. So I'm looking at the energy rather than the free energy when I do something like this.
Oh, okay.
But it's also Wegener, particularly a student of his, which was his PhD thesis, basically, had a look at the low temperature expansion for this model and showed that the state that had these planar flips of spins was still the lowest energy state, even at finite temperature.
Thank you.
And again, at the danger of going off piste, the dual of this 3D Plaquette Ising model is also an interesting beast. And it also possesses this planar flip symmetry. So what you want to do whenever you're dualizing a lattice model, so I'm talking about the usual Kramers-Vannier duality here, rather than something fancy, none of these weird string theory dualities. If I want to dualize the 3D Plaquette Ising model, I do a high temperature expansion, and then I try and get that back as a low temperature expansion of another spin model. So if I do a high temperature expansion of the Plaquette Ising model, what I get is a sum over closed surfaces where I've got an even number of plaquettes at any vertex on the dual lattice. And I can generate this as the low temperature expansion of an anisotropic Ashkin-Teller model, bizarrely. So now there's two flavors of spins living at vertices. These guys only interact along, say, the x direction. These second flavor of spins only interact, say, along the y direction. And these spins, where I've got a 4-spin interaction, that's what makes it an Ashkin-Teller model instead of an Ising model. These spins interact along the third direction only. And if you do a simulation of this model, you get back exactly the dual of the Plaquette Ising model. So this guy will have, again, a first order phase transition, and it'll still have this weird scaling that isn't scaling as the volume. So I've still got this degeneracy in the low temperature phase. And again, if I forget about entropy effects, if I forget about temperature and just have a look at the energy, I can see that I can flip planes of spins in this anisotropic Ashkin-Teller model as well. I just have to choose whether to flip the sigma or the tau spin or both of them in the different directions. So I get the same degeneracy in the ground states and the low temperature phase. And I could keep banging on about duals of these models. Curiously, there are several ways of writing the dual to the Plaquette Ising model in 3 dimensions. I can introduce it. Sorry.
Can I interrupt it?
Aye.
So when you say that you're doing the low temperature of the dual model, this presumably would correspond to the high temperature of the
yes,
Plaquette model. Is that, or are you?
Exactly. So just as you would for standard Kramers-Vannier duality with the ordinary Ising model, you'd be playing exactly the same game. So if I take the low temperature expansion of this guy, it'll look like this high temperature expansion here. Strange but true. And it does look a bit odd because this guy's anisotropic, whereas I've started out with an isotropically coupled Plaquette model. But you count things up and it worked.
Okay. Yeah.
And if you don't believe me, you could believe Wegener, who originally worked this out. So that's the lattice gauge theory, Wegener. So he knows what he's talking about. In fact, bizarrely, you can write down other spin models that are equivalent to this anisotropic Ashkin-Teller model. If you introduce a third flavor of spins, you can make it look a little bit more symmetric. So this is a model that's got 3 flavors of spins living at each vertex of the cubic lattice, but the spins interact anisotropically. So this pair of spins only interacts along, say, the x direction, this pair along the y direction, this pair along the z direction. You can use a decoration iteration transition relation to stick a spin on the links between these and split them up like this. So there are various different ways of writing this dual, and they all display this degeneracy of the low temperature phase where you can flip these planes of spins. So for all of these spin models in the large, a ground state or a state in the low temperature phase even looks something like this. So it's not paramagnetic. You've still got some sort of correlations along planes in these different directions.
Sorry, yeah, I'm still trying to grasp why they all have the same low temperature behavior. Is it the fermionic nature of these that's giving me that? I mean, you have the degeneracy being the same at low temperatures for dual models, which means that it's the same at high temperatures as at low temperatures.
I should have swapped the high and the low when I was talking about it.
Oh, so I'm misinterpreting. It's not how it's not that they. Okay, the high temperature is okay. All right.
So what's going on with all of these models? Why do you see this strange scaling whenever you do the numerical simulation, whether it's the 3D Plaquette Ising model or the other ones? Normally, when you're working out these scaling relations for these models, for instance, with a Q-state Potts model, the Q is a constant, the number of low temperature phases. But what you're seeing here is that you've got an exponential degeneracy. So it's 2 to the 3L roughly for the Plaquette Ising model. You can flip your planes of spins in any of the 3 directions, and each plane of spin can be plus or minus. You're flipping these things. So you've got a degeneracy that looks like this for your Plaquette Ising model. So if naively, you just take your relations that you wrote down, say, for your shift in your estimate of the first order transition point, and you replace the Q that you had sitting in there with something that goes exponentially as L. So it's still sub-extensive. It's not a volume that you've got here. It's an L. So it's not L cubed. It's not e to the L cubed. It's e to the L. If you put that in here, what you get is an L to the D minus 1 instead of L to the D. So it's not volume scaling anymore that you're seeing for this first order phase transition. Whenever you've got an exponentially degenerate number of ground states, low temperature states, you shift this by 1. And that's exactly what you saw in the simulations. So you didn't have an L cubed, you had an L squared. So that's the unique selling point of this Plaquette Ising model. You've got this strange degeneracy in your low temperature phase, and that's giving you a different sort of scaling here. So the PhD student was right. It really was L squared instead of L cubed, and that's the reason for it. So the first observation, the 3D Plaquette Ising model and the duals display a subsystem symmetry. You can flip not globally, but planes in the model. And just to finish off, what's all this got to do with what Patricio was talking about a few weeks back? Let me sidestep and move away from the Plaquette Ising model and very briefly introduce an old favorite of many people, the toric code. So what's the toric code? We're talking about quantum spin models now. So I've got quantum states, qubits, say, living on the edges of a lattice, zeros or ones, inside kets. And the Hamiltonian in this case is given by these two terms. So one of them is a vertex term like this. It's a product of Pauli X matrices, and I've called them tau X here, around this vertex. And there's a Plaquette term as well, product of Pauli Z matrices. I've called them tau Z, around this Plaquette. So where I write a product here for these matrices, I mean tensor products now, instead of just multiplying them out. So we've skipped over into the realm of quantum spins instead of classical spins. And the Hamiltonian for this guy, the toric code Hamiltonian's given by this. What does ground state for a model like this look like? Well, I could take either the ground state for the A or B term as my starting point. So if I take the B term as the starting point, That's got tau z's in it. So the ground state will be a product of all of these zero kets. And I've still got to take account of the vertex term, the AV. I want that not to be -1. So I can project out the ones that are -1 by including this projector for all of the vertices. And if I have a look at what a state like this looks like, it's a loop soup. So the ground state of my toric code is a loop soup. It looks something like this. And I'll forget about the interesting bit of the toric code, what the boundary conditions tell you about periodic boundary conditions. Excitations in the toric code, well, I break the loops. So I can get electric excitations by taking a string of the poly Z matrices and not closing them. So a string of tau z's will give me a couple of electric excitations at either end of that string. And a string of tau x's, blue here, will give me a couple of magnetic excitations sitting in the middle of the plaquettes here. And if I braid these excitations, they're created in pairs from these strings. I need to drag the strings along with them, and taking the poly matrices through each other will give signs, depending on how I braid these things. That's why the toric code's interesting. So the E and the M, so if I've just got, say, an E string, and I braid it with itself, it's just poly Z matrices, nothing happens. If I've just got an M string, braid it with itself, it's just poly X matrices, nothing's going on. But if I take them through each other, I'm going to exchange or anti-commute X's and Z's. So there's going to be a minus sign coming into that. So the E and M are bosonic with respect to themselves, but if I take an E for a walk around an M, it gives a -1 phase. So the interesting thing about the toric code is it's got anyons as the quasi-particle excitations in it. And of course, there are other interesting things as well. There's the topological degeneracy of a ground state, etc., etc., etc. Great. So why have I started talking about toric code suddenly in the middle of a seminar about the Plaquette Ising Model? Bear with me, we're nearly there. How do I get the toric code? So it could just emerge fully formed from Kataev's brain, which is what it did in the first instance, I think. Or I can think about it lurking inside something more familiar, which suits me, coming from a lattice gauge theory direction. Let's go back to the standard Ising model with nearest neighbor interactions. Let's make our life simple. Let's go to 2 dimensions now. So we're on a square lattice instead of a cubic lattice. And we're talking about quantum spin models now. So I've still got poly matrices floating about. And let's look at the quantum version of the 2-dimensional Ising model. So there it is. There's the nearest neighbor interactions. And with a quantum spin model now, I put in the spin flip operator like this for the external field. So here's the 2D quantum transverse Ising model. The poly X mate, and you notice these are sigmas now instead of taus. There's a reason for that. The poly matrices, the X matrix will flip the spins. This thing will measure the spin basically and give you this energy term here. This thing's got a global symmetry. So in the high temperature phase, the first term's basically 0, and I can flip the spins to my heart's content. It doesn't make any difference to this bit. But if this term's sitting here, and I try and flip the spins, it's going to affect this coupling. But I can tidy that up by introducing another set of spins. So I can gauge my symmetry, and I can turn my global symmetry into a local symmetry, turn this into a gauge theory. So I can gauge the global symmetry of the 2D quantum Ising model by inserting a spin between my 2 original spins. And if I take a product of these guys, nearest neighbors around the plaquette, it would be 1 here. If I've got this sitting between the spins now, it's no longer 1. I would like to control that. So I would put in a dynamical term for the tau now. So the product of these sigmas around the plaquette is 1. It's not anymore if I include the tau, but I can control its value by including a product of the tau spins around the plaquette. So as the j goes to infinity, that pins these things down. And if I want gauge invariance, what I want to impose is this condition. So this is Gauss's law on my lattice. If I flip a spin at one site, changing the gauge spins on the edges that are adjacent to that site, that touch that site, should give 1. So Gauss's law is imposed like this. So what? Well, if I have a look at the high temperature phase, is that right? Yeah, if I take T to infinity of this guy, this goes away, and I'm left with these two terms. For gauge invariant states, I can trade in the sigma x for a product of the tau x's, because sigma x, product of the tau x's, is equal to 1, Gauss's law. And what I'm left with is this, which is the toric code Hamiltonian. So the toric code Hamiltonian is hidden in Z2 lattice gauge theory, quantum lattice gauge theory. If I look at the gauge invariant sector of Z2 lattice gauge theory in 2 dimensions, it's the toric code. It's already sitting in there. And there's a nice series of lectures by Sakdev where he looks at quantum lattice gauge theory in 2 dimensions from the point of view of the topological gauge theories, like the toric code, where he uses this point of view to talk about the different phases of the gauge theory. But toric code is sitting
What's
there.
the reference again, just?
I'll show you afterwards. There's a nice series of lecture notes by Sakdev.
Okay.
Actually, I don't think they're meant to be in the public domain. They're on a Harvard website for some lecture course that he gave, but you can see them from the outside. So fine.
Okay.
Okay. So
By Sashdev.
yeah, and the other person who's written a nice set of notes about this is Z Chen at Caltech. So getting topological models from gauging other models. So the toric code is Z2 lattice gauge theory in the high temperature phase, whenever you have a look at gauge invariant states. So what? And how do you get the continuum theory from that? Well, a caricature of the continuum theory for the toric code is you have a look at your string operators for creating quasiparticles. You write them as Wilson lines in some continuum theory. And then you have a look at which continuum theory action gives you the right properties for your quasiparticles. And the right properties are given by this Chern-Simons theory in 2+1 dimensions. So let me skate lightly over that as time marches on. What about this X-cubed model that Patricio was so reluctant to talk about a few weeks back? So what's that? Well, a picture is worth 1,000 words. So it's a bit like a 3D version of the toric code, except it's not a 3D toric code. That's another model with a different set of terms in the Hamiltonian. This beastie has got poly X matrices around all of the edges of a cube. And it's got 4 terms. And these are very badly drawn here by me. Apologies. These crosses are meant to be in each of the 3 planes in 3 dimensions. And they've got poly Z matrices sitting on the edges. So there's poly X matrices sitting on the edges here. And these interaction terms have got poly Z matrices sitting on the edges. So this guy is meant to be in the, what direction is that? That's X, that's Y. This guy's in the XY plane. This guy is in the YZ plane. And this guy is in the XY plane, if you see what I'm trying to draw here. And the Hamiltonian for this beastie is given by this expression at the bottom here. So the A is the cube term here. And then each of these terms are denoted by a B, like this. So again, this could spring fully formed from somebody's imagination. It was Vijay, Haah and Fu in this case, who came up with this strange looking thing. Or you could find it hiding somewhere more familiar. And Oh, let me say something about the model. It's interesting because the quasi-particle excitations in this aren't anyons. They're restricted mobility quasi-particles in 3 dimensions. If I look at the electric excitations, so I think about putting a tau z along a single edge in the lattice, what's that going to do? Well, it's going to interfere with the x's here. So you're going to get excitations in these cubes. But if you look at a single one of these tau z's, it's going to affect 1, 2, 3, 4 cubes. So you're always going to have to create these excitations in 4s, not just in pairs in this model. And there's no way to get them to move without putting more of these red lines in. You need to create them at the edge of these membranes. So these are excitations that can't move without putting more energy in. They're pinned in the lattice, quasi-particle excitations. That was the tau z's. That's a terrible choice of color there. I don't think anybody can see that. In blue, there's a tau x. The magnetic excitations, on the other hand, can move. If I have a look at these cross terms here, I can see that sticking in a tau x on one of these edges is going to interfere with 2 of these. But it's not going to interfere with this other one because it's pointing in the other direction. So excitations coming from putting tau x's along the edges can move in a single direction, but they can't change direction. So with a severe lack of imagination, these excitations were called lunions or linons. If you put 2 of these guys together, and you can amuse yourself by hopping cubes around on the lattice, you can find that they can move in pairs, in planes. And these excitations paired up were called planons. So there's all kinds of interesting quasi-particle excitations in this model. And Denjo's getting twitchy there, but don't worry, I'm nearly finished. I'm drawing to a conclusion. So I'd started off talking about this Plaquette Ising Model. I veered off at a tangent to start talking about the toric code and this X-cubed model that you heard about already a few weeks back. What's the connection? Well, we got the toric code by gauging the standard nearest neighbor 2D transverse quantum Ising model. Let's gauge our Plaquette model, or a quantum version of our Plaquette model, and see what we end up with. And you can probably guess what the answer is. So if I turn my Plaquette model into a quantum spin model, the Hamiltonian term will be the sigma z's, the poly z matrices that measure the energies, and there'll be a flip term. There'll be a sigma x or a poly x that flips the spins, the quantum spins on an edge. There was a subsystem symmetry in this model. There wasn't a global symmetry. Let's try gauging the subsystem symmetry. So what did I do when I gauged the symmetry in the standard Ising model with nearest neighbor interactions? I plonked a gauge spin in the middle of the interaction term to make sure that I could still maintain the invariance. Let's plonk a gauge spin in the middle of the 4-spin interaction term here. And we also introduced a flux term in the case of the toric code by having a look at the product of my interactions around a plaquette, which would have been 1 if I didn't have the new gauge spin. But with the gauge spin included, that gave me a plaquette interaction term for the gauge spin on the edges. I'll need to do something similar here. If I take a product of plaquettes, 4 plaquettes around the edge of a cube, in the original model without the gauge spins, that would be 1, because I'm multiplying out these pairs of spins and they're squaring out to 0. But I've included the flux terms now. So I've now got flux terms from the tau spins in this case. So if I put all of that together, there's the original Plaquette model with the gauge spin. Here's the introduced flux terms. I'm still going to want gauge invariance. So now if I flip a spin all of the Plaquette spins that touch it have got to be equal to 1. So there's Gauss's law in this new system. And if I take the limit of high temperature in this Plaquette spin model and make use of Gauss's law, I end up with the x cubed Hamiltonian. So just to repeat that, way back here, I gauged the standard Ising model in 2 + 1 dimensions, quantum Ising model. I had a look at a high temperature limit, gauge invariant sector, and I got the toric code. Now I take my Plaquette Ising model, which doesn't have a global symmetry. It has this subsystem symmetry where I can flip planes of spins. I gauged that by putting in appropriate gauge spins in the appropriate places. I had a look at the high temperature phase of that, imposed Gauss's law for these spins, and I ended up, in this case, with the x cubed model. So it appears in a similar fashion to the toric code appearing for the standard Ising model from the Plaquette Ising model by gauging the symmetry in that case. Second and third observations, gauge a global symmetry, get the toric code, gauge a subsystem symmetry, and we get the x cubed model with all these interesting features like fractons. And you can play this game with other models as well. So I refer you to the original paper by Vijay, Haah and Fu on this. So you can take other models with complicated interactions, gauge them, and get different interesting fracton systems, where you've got restricted mobility to the quasiparticles in those systems. And Vijay, Haah and Fu recovered other known models that had simply been constructed by hand beforehand from this gauging procedure. Very, very nearly done. Continuum limit for the x cubed model. Well, you play the same kind of game. You look for Wilson lines that give you the behavior of your quasiparticles. And it turns out, and this was what Patricio was talking about, that it's a BF theory in the continuum that corresponds to your x cubed model. So if you're taking a Zn version rather than a Z2 version of the x cubed model, this BF theory will give you the right complement of excitations in your model. Or you could do it the hard way. You could take the continuum limit of your x cubed model and actually show that you end up with this as well, which has been done by several people. So, Binus, references, original and best. So Wegener invented lattice gauge theory. He also invented these peculiar models with subsystem symmetry as well. Quite a few years back now, 1994, with Savitty. So Savitty formulated a string model originally, and he was interested in putting this in a cubic lattice. So he had a string model where you all composed of triangles, where you only weighted bends in the triangles, sort of extrinsic curvature. And Savitty paid a visit to Wegener, I think, and they got talking about how you turn this into a spin model, and this was the result. The original paper on fractons that really set off the current torrent of work on it was by Vijay, Haah and Fu. And this is a terrible name. It's already been used for phonon excitations on fractal lattices. So if you Google for anything that says fracton before 2016, it'll be for a phonon excitation on a fractal lattice. If you Google for anything that says fracton after 2016, it'll be for a quasiparticle with restricted mobility. And there are loads of reviews about it. This is already out of date, so that they're more recent ones. If you're interested in the continuum theory, which I'm glad to hear nobody has asked me any questions about, since I know even less about that than I do about the rest of this. Z Chen, Michael Pretko, Kevin Slagle, and also Seiberg has written quite a bunch of papers recently with one of his PhD students or postdocs, Shuheng Shao, about continuum theories that correspond to these fractons. And the important point for these continuum theories is that you don't impose a full rotational symmetry on your fields, which was Patricio's starting point, actually, when he was talking about the sorts of models that you're interested in that case. Time is sort of separated out from the spatial symmetries. So that's why he was interested in introducing ideas from the non-relativistic gravity, these various weird limits in gravity, like Carolean gravity. And I've already talked for far too long, so let me stop there. Okay, done.
Well, thank you very much for a fascinating tour through and a very eloquent tour through a lot of these lattice models. Thanks again. We're rather silent in this format, but
Right, so
the floor is open to questions.
You're not allowed to ask me anything about the continuum theories that I know.
I will get to that in a minute.
Yeah, I have a question. I have a question indeed about the toric code and XQ model. So actually, when you say that the toric code is described by Chern-Simons theory, actually should be a BF theory, right?
Well,
because
yes,
the toric code is time reversal invariant.
It can be described by a BF theory or a Chern.
Yeah. Well, usually the Kitaev toric code is time reversal invariant, so that is the usual feature, right?
I should have called that a BF theory as well. So in that case,
the thing that yeah. So now in the X cube
is I'd be having two fields, just like I had. I don't want all of this nonsense. Hang on, where are we? Yeah.
Yeah.
So I'd be having two fields, but I wouldn't be introducing all of these weird extra indices.
Yeah. No, exactly. So if
no, you're quite right.
In this slide, indeed, that you are showing now, the BF theory actually should be also a BF-like theory because it's not fully topological. I mean, the fractons are not fully topological in the sense.
I mean, you can see that.
So yeah, so then there should be somehow a sort of hybrid situation, which even the Wilson loops, right, are not really Wilson. Well, Seiberg called them Wilson stripes, something like that. It's something.
There is a dependence on the
the foliation, right? So I'm wondering, do you think that this is this losing of topology is due to the gauging of a sub symmetry instead of the full symmetry? Do you think that is the reason?
I mean, I'm no expert, but that's how I thought of it.
Okay.
And again, somehow the geometry of the lattice matters in these things, because you wouldn't have these particular collection of indices if you didn't have a cubic lattice to start with.
Exactly.
Seiberg and Schei depends on their lattice.
No, exactly, because also there is another thing that even the fully continuum limit, so you don't recover the full Lorentz invariance. So this is another difference.
No.
So they're intrinsically Lorentz broken, even the continuum limit. So
which is why it's interesting for these people who do Carolean gravity.
Yeah, it's true. I'm working with Patrizio, that's why I'm a little bit familiar in this field. Do you think so? Now I remember also one of your previous paper about the Gerb lattice model that I think you mentioned.
Funny you should ask me.
So Gerb, exactly. How are you? Yeah, I would like to hear something.
This question isn't a plant. It's not a plant. So previous paper, it's rather similar, but the details are a little bit different. So if you have a look at the spin models, say classical spin models, that would give you these. They're defined. You've got spins that are sitting in the center of faces, and Hamiltonian terms that are coming from sums of these faces round to cubes. So you sort of bump things up by a dimension as well. So in this case, what you are getting is a lattice version of two form.
Right. Yeah, exactly.
And again, remarkably, so all of these equations, as usual, nothing of this is original. Wegener wrote all of this down before as well. This is in Wegener's original lattice gauge theory paper. He considered these higher form theories as well, though he was mostly talking about sort of discrete versions of them rather than continuous ones. So you can think about Z2 or Zn versions of these Gerb theories on a lattice as well.
Yeah. Maybe I was wondering if you can mix the two things to have a sort of Gerb fractonic system, because in principle...
some people who have tried this with Continuum
Yeah, in Mosner. Yeah, I think
Yeah,
Mosner in tried it. Yeah.
Mosner I was thinking of actually.
Yeah. But it's very few
How
people.
successful that's been. It's sort of mixing the symmetries.
Yeah.
I haven't thought about what a lattice action would look like for something like that. I mean, there's no reason why you shouldn't. You can chuck in whatever you like into your
No, exactly. I think it will be extremely interesting to have a lattice version of what Mosner have. I think maybe you have already fractons and gerb separated, so I think
I'm
probably
very simple-minded. I'd like to do stuff with sort of plus and minus one spins if I can.
Yeah.
And we didn't know anything about all of these subsystem symmetries when we started out playing this game.
All right.
And I really did think that the PhD student had made a mistake in his simulations and realized what was going on.
Okay.
This fracton stuff came along a little bit later.
Okay.
I mean, from your point of view, are you interested in the symmetric tensor gauge theories?
Yeah. I'm working. So other people claims that fracton are somehow related also to linearized gravity. So there are some claims by other people. So in principle, one can look at also the connection between linearized gravity fractons and the lattice models that is always the starting point, right? I mean, I agree with you that the lattice is more fundamental than the continuum theory. But there are, people propose many different directions for these fractons.
Curious. I mean, Jelle Hartong in Edinburgh has been working on these with his collaborators as well.
Yeah. There are several people now are interested in this relation with gravity. And that's why it came out that also the B field should be an extension of gravity, right? When you introduce the B field. So,
question is how you covariantize the construction of fractons, because you've got
it's true. This is true. But in principle, again, one can think that the Lorentz symmetry start to recover. So it will be a sort of a non-Lorentzian version of the Pauli-Firth theory. Pauli-Firth theory linearized gravity, but it's for spin 2. And people thought, okay, there is one first take the non-relativistic limit of Pauli-Firth, and then try to connect after to fractons, just because Lorentz is never there, right? Lattice or continuum. I mean, this is a possibility again.
I mean, the other place to look for connections, of course, is in solid state theory.
Oh yeah. No, of course, the solid. I'm a solid state physicist actually, but I have to say that there are not so many experiments on fractons from the condensed matter point of view. The problem that these fractons are very highly constrained system, so requires a lot of. I mean, people claim, for instance, Pretko and claims that there is a mapping between fractons and a defect, a dislocation in crystals. Yeah. This is a little bit more simpler to understand because dislocation, declination are everywhere in lattice system. I mean, in solid state also. So, but this is a classical mapping. It's not really quantum. So the question, if one wants to do really a fully quantum fractonic system. So for instance, Patrizio mentioned some gauge theories, and they requires not only the Gauss law for charge, but also the Gauss law for dipole. So one has to think about a condensed matter system with a dipole momentum conservation together with the charge conservation.
So that's a lot of constraints.
Yeah, it's a lot. It's quite a lot in principle because the dipole conservation is something a little bit unnatural in many. I mean, can be built artificially as a system, but not in. It's much more hard to see in really solid state devices. But again, as you say, many people are interested in this fractal, and from different point of view, Seiberg is doing his job on the more the field theory, string theory side. I mean, it's a very active field. I have to say. So.
I'd be interested in further classical examples of.
You
get these subsystem symmetries. You can construct them in clock models as well.
If
you've got a clock,
that's right.
The interactions that you've got, you can have planar symmetries or even linear symmetries in those as well.
Okay, that is interesting.
For classical spins, and you get some degeneracies as you see.
Absolutely. For Potts model, I mean, it would be interesting to beyond icing, you mean? Yes. It's,
Oh no,
would be
sorry, I
also-
said clock models.
the clock model. Yeah. Okay. Sorry.
Yeah.
Okay. Yeah.
Excuse
Absolutely.
Excuse the accent.
Okay.
I didn't recognize the top of Brian's head there. He's had a very severe haircut.
Can I ask one maybe go back to a very basic question?
Yeah.
In the Ising model, I can impose the constraint that sigma I squared is 1 as a delta function on a continuum field.
Yeah.
And if I smear it a little bit, I get a lattice version of a 5-4 theory.
Uh-huh.
Now, if I do the same thing here for your spins, I mean, if I do it in the lattice version there, you can see that the nearest neighbor interaction of the original Ising one is the essential part of the
So all
Laplacian.
the continuum field theories that correspond to these things are always higher derivative.
Yeah, yes, I can see that. I mean, this comes out very naturally from the way I'm thinking about it.
Yeah.
There, if I smear it as a Gaussian there, I put in, I'm still going to get a 5-4 interaction as a local interaction.
Yeah.
But the original Hamiltonian that you wrote will be now related to derivatives, and I'll have derivatives around my plaquette.
Yeah.
I mean, has somebody looked at it from that point of view? Because I would hope to be able to see the.
Don't know. No, I mean, there are. Have a poke around in Seiberg and Schau's papers. There's a whole string of them. They have various scalar field theories that display these sorts of symmetries, subsystem symmetries. But
yes, this should give scalar field theories that would display something. They would have the same features, but they will be higher derivative. They'll have fourth order derivatives in the kinetic term or in the quadratic.
But they don't arrive at.
It's not even a quadratic term. They'll have no kinetic term.
Yeah. They don't arrive at these things by trying to take the continuum limit of a Plaquette model in that kind of way. They're sort of constructed
Right. Okay.
by fiat. Yeah, actually, I've never thought of that.
I'm just going to say goodbye because I have to.
Yeah.
I don't get to admire your books any longer.
Well, at least
Yes.
Or the hat.
I'm not sure that yeah. Okay, take care, Charles.
See you.
I'm not sure Howard Sojonovich transformation would quite work there, but maybe you could do something there as well.
I don't know.
Anyway, that's
They're a curious class of models. People hadn't really thought about these subsystem
Yeah.
symmetries before in quantum field theory. I think the person who's really pushed that is Seiberg. So quantifying it, and because of course he had done a lot of stuff on global symmetries before, so you had the right kind of
Sure.
language for looking at this sort of stuff.
I was actually waiting for Dendro to stop the recording so I could ask a question related to that.
I'm the wrong person to ask. Yeah.
Well, I mean, I'm going to ask it in a simple way, the way it came to my mind. I'm a particle physicist, so I always.
So was I once upon a time.
Oh, really? Oh, wow. Yeah. So, I mean, I always thought, why don't we have discrete symmetries as gauge symmetries? I know. So it's very good to see. Actually, no. Yeah.
Well, these. I mean, you are gauging Z2.
Yeah. Yeah. I mean, in the standard model, you don't do that. Right, as a particle physicist, I'd never seen it. Whereas, yeah,
the condensed matter theory, people are very comfortable with doing stuff like this.
it kind of relies on a lattice. It's hard to see how to do it.
Yeah, so I guess if you're coming from condensed matter theory, you're used to thinking about lattices of things. So it's, but well, no, does it?
Naively, it does, but if you can.
So what about all these fancy string theorist ways of thinking about global symmetries? So they can.
Yeah, I mean, global symmetries or I can deal with global symmetries, discrete or continuous, doesn't matter. Yeah, like I always struggled if
she wants to gauge.
Yeah, I want to gauge a discrete symmetry like Z2, And then again, as a particle physicist, as a gauge symmetry, would I have a gauge boson associated with it? What would it look like?
Well, so if I was playing with the toric code, these are C2 gauge fields, or the A is. So, I mean, the usual way people think about a Z2 toric code is they start thinking about a U1 one to start with. So in that case, your fields would be an E and an A, and the A would be going between 0 and 2 pi, and the E would be any integer value. So you've got sort of a router quantum thing sitting on your lattice side. And then to go to Z2, they talk about Higgsing it, so you restrict the A either 0 or pi instead of going from 0 to 2 pi. And the E now doesn't go from 0, it's not 0 up to anything, it's just 0 and 1. So what am I saying? So
kind of like
write down what you would have thought of for a continuous theory, and then restrict your gauge fields to some set of values. Brian's being very dyspeptic there.
Yeah, you would say from a Z2 symmetry, you would have 2 gauge bosons, the A and E?
No, one of these is the sort of variable, and the other one's its conjugate. This is the Hamiltonian way of doing things. So one's the variable and the other one's the momentum.
Yeah, that makes a lot more sense, because a U1 symmetry, if you break it or Higgs it, you will have 1 gauge boson.
Yeah.
It's surprising if you have a Z2 and then you get 2. Cool. Well, thank you so much. It was a very good talk. I really learned a lot.
Yes, it was an excellent talk.
I'm not
Thanks,
sure I convey very much information.
Oh, you conveyed quite a bit. I'm going to stop the recording while we're still praising you.
God, I didn't realize we were still on stream. Oh no.
Thanks again, Des.
Yeah. Okay. Shall I stay online?
Getting back to